Hi everyone, this is Tom Yang. Welcome to Math at All. Today we're going to prove one of the commonly used formulas on the AMC exams, which is the hockey stick identity. And today I'm going to write down the formula and to prove it using an example. So let's write down the formula first. It is sigma I choose R all the way from I equals to R to K. That equals K plus 1, choose R plus 1. Okay? So for those who are not quite familiar with the sigma symbol, it just means the sum of all those terms from here, I plus R, to K over here. And let me write down an example. Let's say 7 choose 3, okay? And according to the hockey stick identity, that would equal to what? That would equal to um, 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus 5 choose 2 plus 6 choose 2. Right? So if you sum all those up, that would equal to 7 choose 3 with K plus 1 choose R plus. All right, so uh, I've seen a lot of people proving this formula using the Pascal triangle. All right, so what they basically did was they first draw out the Pascal triangle. Here, 1, 3, 3, 1, 1, 4, 6. Yeah. So I'm gonna stop here because that's all I need. So what basically happened was if you were to sum up all the elements in a diagonal line, starting with 1, that would equal to the next element down diagonally in the opposite direction. So what I mean is, okay, you choose a 1, okay, let's say you choose this one over here, and you go diagonally, and let's say I stop at number 3, okay, I stop here, and I'm going to sum up all the numbers in this diagonal, okay, and that the sum will equal to the next element down diagonally in the opposite direction, which is this number, right? And 1 plus 2 plus 3 is indeed 6. And that does not only work for this case, that works for all cases, as long as you're choosing numbers in the same diagonal line starting with 1. All right, like here, 1 plus 3 is equal to 4, right? And that is actually a very interesting property of Pascal triangle, but we're not going to prove it using this logic. We're going to use another logic, might not be known by a lot. And so before I start proving it, I'm going to draw um, some pictures. I'm gonna draw 7 colors. To I'm gonna use blue. Okay. So I'm going to use. Let's say I have 7 balls. Okay, 7 balls labeled with numbers 1, 2, 3, 4, 5, 6, 7. Okay. Let's say they are distinguishable. Okay. Meaning that none of the balls are identical to each other. They're distinguishable. And I'm going to ask you, okay, how many ways are there to choose 3 balls? 3 balls from the 7 balls above. And if you learn a little bit of combinatorics, you would say, oh, that's so simple. It is just 7 choose 3, right? And you're correct. That is the answer to this question. But we are going to use this example to establish my proof of hockey stick identity. How would I do so? Well, so let's say okay, before I do that, let me copy down, copy the balls so that I can better illustrate it. Okay, so let's say, oh, I'm not going to use this simple method. I'm going to use a convoluted method. So what I do is the, I'm gonna start from the ball with the highest number, which is 7, right? And let's say 7 is the number that has to be chosen, okay? let's say this number has to be one of the three balls to be chosen. And what are we left with? We're left with a pool of 6 remaining balls, right? And we can only choose 2 of them from 6 remaining balls. And how many cases are there? How many different cases are there? Well, that will be 6 choose 2, right? Because there are only 2. We can only choose 2 from the 6 remaining balls. And 7 is to be chosen. Like, this is fixed, right? So it is 6 choose 2. Okay, let's move on. We are going to start with the second highest number, which is 6. All right? And we're going to be left with a pool of 5 balls. And we're going to choose 2 numbers from that. Well, now here you might ask, how about 7? Why aren't you considering 7? Well, that's a very good question. In the first case, I already said that 7 is the number that has to be chosen, which means in the 6 choose 2 case, all of the cases already contain the case in which 7 is chosen, which means the case that contains 7 is already counted. Like all of them, all the cases that contain 7 are already counted. So in the following countings, we're not going to consider 7, because if we were to count 7 again, that would be overcounting, right? So if we choose 6, let's move on. If we choose 6, we're left with 5 balls, and we're going to choose 2 of them from that, right? What would we have? Well, we're going to have 5 choose 2 number of cases, correct? And if we do this repeatedly, we're going to end up with 6 choose 2 plus 5 choose 2 plus 4 choose 2 plus 3 choose 2, all the way down to 2 choose 2, right? And we're not going to have 1 choose 2, because that just does not make sense mathematically. And according to this example, 1 choose 2 also does not make sense, because we're going to end up on which number? We're going to end up on the number 3, right? And in this case, we only have 1 and 2 left. So there's only one case, which is the 2 choose 2, right? So if we were to sum that up, that is equal to 7 choose 3. If you were to do this mathematically. So what is 6 choose 2? That is 6 times 5 over 2 times 1 plus 5 choose 2 is, I'm just going to skip some steps. This is 6, this is 3, okay. What is 7 choose 3? 7 times 6 times 5 over 6, okay. So it will be 15 plus 10 plus 6 plus 3 plus 1. And that is 35. Yes, exactly. Left side equals the right side. That is mathematically correct. So yeah, here is how I use this example to prove the hockey stick identity. And if you have better ways, you're always welcome to share them. And that's all. Thanks for listening, and I hope that you learned something. Bye.